Hello everyone. For our final lesson in engineering statics as part of our college course, we're just going to be going through a practice problem that combines the first and second moments of area. For those of you who are taking a class called dynamics or even studying center of mass in Calculus 3, multivariable calculus, you'll see similar things to what we're actually going to be talking about here, but this is for statics, where for the most part, density is a constant, and therefore our problems are noticeably easier. What we're going to cover is the statical, Qy and Qx, the centroid, x bar and y bar, and then our three types of inertia, Iy, Ix, and polar inertia, J. For defining our problem, for the area defined between the curves f of x and g of x within the range x equals 1 to 2, determine the statical, the centroid, and the inertia of the area enclosed between. Our top function f of x is going to be 2 over the cubed root of x, or x raised to the 1/3, and then our bottom function, g of x, will be the square root of x, all of that divided by 2. So 1/2 times the square root of x. For our equations of the statical, or the first moment of area, that will be qy being the integral of x times the difference of our top function minus the bottom function, dx. And qx will be 1/2 times the integral of the difference between our top function squared minus our bottom function squared, dx. For the statical, the units will be meters cubed because we're talking about area. If we were talking about mass, then think kilometers cubed or kilograms cubed. Now, for our equations of the centroid, or the center of area in this case, area is going to be the integral of our top function minus our bottom function, dx. And its units will be meters squared. The centroid, x bar, y bar, well, x bar will just be our qy divided by the area, and y bar will be qx divided by the area. And once we do that, our units would be in meters. Similarly, if we were talking about mass, then we'd be working with kilograms eventually. Lastly, we have our equations for inertia, which is the second moment of area. Since there's more than one, that's why it's called moments of area. Iy is defined as the integral of x squared times the difference of the top function minus the bottom function, dx. Ix is defined as 1/3 times the integral of the top function cubed minus the bottom function cubed, dx. And then J, polar inertia, we can easily find that by just adding up Iy and Ix. And this would be similar to torsion about our centroid. The units for all types of inertia, when we're talking about moments of area, would be meters to the 4th power. Now at the bottom here is just a plain diagram showing our top function over our bottom function from the bounds 1 to 2. In reality, if you had this problem, you would not already have the center of area defined as 1.29, 1. That would be something that you would have to find. And here's how we're going to figure out a few of these equations here. Qy, that's pretty simple. All we're doing is taking our difference of our top function minus the bottom function. So 2x raised to the -3/2. That's bringing our bottom function, square root of 2 over the square root of x raised to 3. Bring that up to the top here by just making a negative. 2x raised to -3/2 minus x raised to the 1/2 over 2. and then all that multiplied by x. Before we solve our integral, let's just multiply x across so that we have, once we do that, we're taking x to the first power plus x to the negative 3 halves. Multiply by 2 is 2x to the negative 1 half. And then x to the first power times negative 1 half, x to the 1 half. 1 plus 1 half gets us negative x to the 3 halves over 2. Now if we take the integral from 1 to 2, this gets us 2 times 2x raised to the 1 half minus 2 fifths times x to the 5 halves over 2. All we did was take our exponents for our x's and raise them by 1. And going from 1 to 2, that will give us approximately 0.7255 meters. Let's see, meters cubed. Now qx, the statical about the x-axis, that will be 1/2 times the integral from 1 to 2 of our top function, all of that squared, minus our bottom function, all of it squared. We're taking the difference of squares. A common error here would be taking the square of the difference. Instead, square both parts first, then subtract. Well, not too hard to do. When we take an exponent and we're squaring it, we're basically multiplying those two numbers. So we take 2x to the negative 3 halves, all that squared, gives us 4x to the negative 3. And then x to the 1 half over 2, all that squared, gets us x over 4. And now we're just subtracting those two terms. And we'll also, outside the integral, multiply by 1/2. Doing this integral from 1 to 2, we get 1/2 times the quantity of 4x to the negative 2, all divided by negative 2, minus x squared over 4 times 2. All that going from 1 to 2. And if we do this correctly, we get approximately 0.5625 meters cubed. Even though this cuts off here, I can see the rest of the number right here. To get our centroid, we also need our area. So the area would be going from 1 to 2. That would be the top function minus the bottom function, dx. Top function being 2x to the negative 3 halves, which becomes negative 2 times x to the negative 1 half. And then the second part of our integral was x to the 1 half over 2, which once we integrate, that becomes x to 3 halves over 2, all that multiplied by 2/3. Now we're taking the first half minus the second half of our solved integral from 1 to 2. That can be simplified further as negative 4 over the square root of x minus the square root of x cubed over 3 from the integral 1 to 2. And that area comes out to be 0.5621 meters squared. Now the centroid is pretty straightforward. X bar is just taking qy divided by the area A, and that will come out to about 1.29. Y bar, the centroid's y coordinate, will come out to qx divided by A. So 0.5625 divided by 0.5621, which is approximately 1. So at this point, if you were asked to actually draw your center of area, your COA, well then just approximate it, where if this is our x-axis 1.2 and 1.4, the 1.29 is just near 1.3 or halfway between those two demarcations. And then we can grow all the way up to 1 on the y-axis, place our dot there, and then label it as our center of area or our COA, COA, and then label approximately what its values are. Now, to finalize this, to finalize our major use of calculus for engineering statics, we have our three types of inertia, which basically helps define how well you can either bend the area about the axis, y or x, or if you try to twist it like a steering wheel, how well will it handle torsion where parts of it is twisting faster than the rest of it. Iy in this case is going to be the integral from 1 to 2 of x squared times the difference of our top function minus our bottom function. Once we take x squared and multiply across, x squared times 2x to negative 3 halves, just taking 2 minus negative 3 halves, that gets us 2 times x to the 1 half, and then x squared times negative x to the 1 half all over 2. 2 plus 1 half gets us 5 halves, so minus x to the 5 halves all over 2. Solving that integral by adding 1 to each of our x components, and then dividing by the new x component, that would end up being 2x to 3 halves divided by 3 halves, or times the reciprocal, 2x to 3 halves times 2/3, minus x to the 7 halves over 2 times the exponent's reciprocal, 2/7. Evaluating from 1 to 2, that gets us 0.9645 meters to the 4th power. Ix is going to be 1/3 times the integral of our top function cubed minus our bottom function cubed. 2x raised to the negative 3 halves cubed will just become 8x to the negative 9 halves. And then x to the 1 half over 2, all that cubed would become 1 half times 3 is x to the 3 halves. 2 cubed is 8, and now we have our subtraction sign. Integrating this gets us 1/3 times negative 2/7 times 8 times x to negative 7 halves minus 2/5 times 1/8 times x to the 5 halves. Evaluated from 1 to 2, that will get us Ix equaling 0.6170 meters to the 4th power. And then our polar inertia, J, is just taking Iy plus Ix, which that would just be 0.9645 meters to the 4th power plus 0.6170 meters to the 4th power, which comes out to 1.5815 meters to the 4th power. When actually reporting your values, what I'm going to ask you to do is report them as they're shown in the original problem. Report your statical as qy, qx, and then set that equal to the two values that you get. In this case, 0.7255, comma 0.5625. Then for your centroid, write parenthesis x bar, y bar, parenthesis, and set that equal to what it comes out to, which is 1.29, comma 1. And lastly, for your second moments of area, do the following. Parenthesis, Iy, excuse me, Iy, Ix, comma J, parenthesis, and then set all this equal to parenthesis 0.9645, comma 0.6170, comma 1.5815, comma, and potentially also including your correct units, which inside the statical we would have for each value, that would be meters cubed. For the centroid, that would be units of meters, and for inertia, all three of these would have the units meters to the 4th power, meters to the 4th power, meters to the 4th power. And thank you all for coming here for this entire semester of engineering statics. It was a pleasure to have all of you for class, and I wish you all the best on your upcoming final exam and last exams. For those of you who are not personally in my class and just watching this video for further assistance, if you have the time, you're welcome to like the video, subscribe to the channel. That basically usually means that you see a rainbow now if I say subscribe. And also, by all means, leave a comment how you are all doing with as engineers plugging in calculus in your engineering classes and not solely in your math classes. No matter what, I wish you all the best, and peace.